Welcome back. And now we implement the examples for the radial basis kernel and, of course, for the sigmoid kernel. Before that, something came in my mind, and I think it's going to be much more interesting to show you. You probably remember that a few classes ago we came up. Let me open here with this example, the polynomial support vector machine. And here we're just testing what I refer to polynomial test 1. I'm going to copy this. Copy. Okay. So paste in another file inside my example 10. This will be for me could be like a test.r, whatever. I'm going to paste. I will load my polynomial svm.r and test just to see if it's working or not. Of course, there is a small change here. It's not classified polynomial because I changed that function to classify.polynomial, not the inverse. Polynomial. Yeah, that's all. I think that's all. We're gonna try it. Of course, you know what? I'm going to close this terminal, close this. Yeah, just one, a single terminal. This is not even necessary at this point. I'm going to open another one, open R, and load my test. Okay. Loading my test, I will run this polynomial test 1 with the default parameters. Polynomial test 1, like this, and run it. Yeah, going to run like this, going to provide some plots. Let's see the plots. I'm going to click here. We're gonna get like the red support vector support vectors in red, sorry. And then the axes, which are not that relevant. And here we've got the hyperplane and of course the gradient-like point of view of our hyperplane. You know what I'm going to do? Take a look at this space. It is centered 0, 0. Those black points are exactly at the center of my space. Okay? So what I'm going to do? I'm going to perform a small modification. I'm going to sum up this matrix X. I'll do this. I'll sum up a vector in that particular matrix. That vector, using that vector, I just add an offset to all my points in my space. That will be like adding an offset, like would be like 5, 5. Just that. And here, when I plot, I do something else. I just define, okay, the X range will be from 0 to the greatest value we've got in the first dimension of X. And in terms of Y, it will be quite similar. It will be like this. The Y range will be from 0 to the second dimension. And I will also plot an AB line using horizontally in 0 and vertically in 0. That's just to see how far we are from 0. Just that. And now I will reload my code and run polynomial test. Yeah, that's my space. Take a look. This is the 0 of my space. I'm not at the center anymore. Take a look. Where are my points? They've got like some sort of offset in terms of my 0. Okay. When I employ my support vector machine optimization using the polynomial kernel, oh, let's see what's going to happen. Take a look. Those are my support vectors. It makes no sense. Let's click to see the x's and to see our hyperplane. Oh, that's really strange. It looks like we've got like some sort of hyperplane that goes like this. It's actually, again, a Gaussian-like function, but it's going like this. It is just like this, cutting this central region as black and all the remaining as green. You know what? The polynomial kernel requires the class that we want to detach from the others to be at the center of the space. So if black points are exactly at the center of my space, I can use it as we did before. But if we don't have those elements at the center of my space, I mean those black points that I want to detach, it's not going to work. Let's try now to change this to somehow to a nearby region. It's going to be 2, 2, the vector that I'm going to sum up. Reloading my code and running once more. Yeah, I'm close, but not that close. What is the problem? All my all my position vectors are like this. I have all position vectors leaving 0, 0 to come to this position, leaving 0, 0 to come to this position, leaving to this point, and to this position, and so on. When you apply the polynomial, the second order polynomial kernel, it's going to compute the length of vectors, the norm, the L2 norm. What is the problem? When you compute the norm of this vector, the norm of this vector, and the norm of this vector, they're going to be quite the same, quite similar. That's why this kernel requires centralization, space centralization. Otherwise, you're going to have this result. Now I'm going to sum up just 1, 1, the vector 1, 1, and try again. Reload my code, run once more. We are somehow we're not at the center, of course. We've got some offset in terms of the center. Let's see the result. Those will be our support vectors. What's going to happen? Take a look. We've got some sort of Gaussian function that crosses my space like this. Inside, it's going to consider as negative, and outside as positive. Let's reduce even more to 0.5 and 0.5, because now you guys will see the effect of our Gaussian-like hyperplane in the original space. Yeah, this is a space. Yeah, we cannot see the others here. Ah, sorry. You know why? Just because I use here x limit equals to 0. Actually, it has to be the minimal value of 0 and my first dimension. Oh yeah, this is going to be perfect. And here is going to be the minimal value considering 0 and the second dimension. Much better. Okay, so reloading. Sorry, I have to click here. So I will reload my code. Yeah, that's reload. It's going to be easier to see. Yeah, reload. What about AB line? What is wrong? About AB? Oh, AB line is right. Ah, yeah. Sorry, I had to use another parenthesis here and another parenthesis here. My bad. Reload my code and run it once more so we can better see what's happening. Yeah, that's a 0 of my space. So vectors, I will have all position vectors leaving from this position and going up to all the other points. In this scenario, we're going to have like some fair result. Those are our position, our support vectors, C's, and our solution. Our solution is crossing like this. It's not like a perfect solution, as you guys might see, because if I want to detach those negative points at the center, I need to centralize my space around the mean of those points. Otherwise, it's not going to work. So sometimes people just get a bunch of points and say, oh, I'm going to use a second order polynomial kernel. Oh, it's not working. Why it's not working? Probably because you haven't prepared your space. However, what's going to happen if I call this test, could be polynomial test dot r, and now I copy the polynomial test, and I'm going to call this copy as radial test. Let's see what happens with the radial test. If instead of testing using a polynomial kernel, what happens if I use a radial kernel? To use the radial kernel, of course I don't have a degree here, you guys remember. I don't have the coefficient. You guys probably remember. Instead of calling SVM polynomial, I will call SVM radial here. Radial. I have to provide gamma, but I don't have to provide any degree and nor coefficient here. Okay, so I have a model. When I apply my classify radial instead of classify polynomial, probably guys remember, that's all. Yeah, I think, yeah. Is there anything else? I'm not sure. Let's try it. Maybe it's not working. Oh yeah, there is something. I need to load my radial support vector machine. You know what? I'm going to leave this R instance, open a new instance just to make sure we are in a different example. Radial test. Oh, there's a mistake. Line 26. There is a small mistake over here. Why? This is right. That's right. This is right. Let's see. Right. Is this right? Yeah, this is right. What I forgot? I'm not sure what I forgot. Is this right? It is. Is right? Yeah, it is. Oh, probably here. No, it's right because I just copied radio SVM. Ah, there's a mistake in my code. Probably radio SVM. Yeah, while loading my radio, it's not the test. It's actually my radio here, SVM. At the line 26. What is the line 26? It is here at the end. Maybe I'm not properly closing my sum over here. Oh yeah, I had to close my sum over here like this, and then sum up beta. I forgot that. I forgot that parenthesis. Sorry, guys. So, loading my test like this, and now we're gonna run it radial.test1 and see what's going to happen. That's my space. Interesting. That's the same space we had before. Clicking. So, did I? Yeah. Okay. Oh yeah. Yeah. Sorry guys. I forgot clicking. So you can see that those are the points I have for my Gaussian kernel. Well, those are the support vectors. You can see that if you use a Gaussian kernel, it doesn't matter if the space was centralized as for the polynomial kernel. It's going to come up with a Gaussian function that can have some offset in terms of my zero. You can see the C's are not relevant, are 10 to minus 17, but you can also see, here is the hyperplane, of course. Here you can see some effects that my hyperplane brings in my space. If I consider a greater vicinity, instead of considering just minus 1/2 to plus 1.5 or 1/2, maybe we could use like minus 15 to plus 15 just to see the effects of the Gaussian kernel, of this radial basis kernel. Let's run it. I'm going to clicking. Those are the support vectors. Clicking once more. X's are not relevant because we don't have a class mixing here. And then we wait for the classification results. Of course, here the plot is not that good because I just decided to increase my range from -15 to +15 because you could see that somehow we've got some effect of a Gaussian around our space. Oh, that's really nice, isn't it? Maybe you could go like from -5 to +5 and things will be just easier to verify, easier to see the effects of our Gaussian. That's something I like to do because it's so interesting. Clicking again and waiting. Okay, let's wait. I'm gonna see the results. This is our Gaussian, okay? The resolution is not perfect, of course. It should be greater, it should be closer. And this is the result we've got with some gradient-like around our Gaussian. That's some sort of perturbation that our Gaussian brings all together. Of course, let's add up some offset. Let's add up like 1.5 here, 1.5 here, and see the results. This is going to be interesting. So, reloading my code and running once more. My 0 is here, clicking. Take a look. Support vectors make sense. Clicking once more. X's are quite small, 10 to -17. And now you're going to see that our hyperplane somehow has like a greater offset in terms of my 0, 0 here and here as well. So guys, please try this in some other data sets and you can verify that we can detach no matter where is located our negative or positive class surrounded by a different class. We can just detach that using a Gaussian-like kernel or a radial kernel. Of course, you can employ, instead of a Gaussian kernel, because here I use the Gaussian function, you can use some other radial-based function. Okay, so we go back now to the sigmoid SVM. I'm going to confirm if I use the parenthesis here. You see, I forgot the parenthesis once more. So there is a parenthesis over here. No, here I used the parenthesis is right. And here's right. Okay, for the sigmoid kernel, it is right. No problem. So I'm gonna copy now our polynomial test and call it sigmoid test.r. Inside the sigmoid test, we are gonna have, of course, we're gonna load our sigmoid kernel, sigmoid based support vector machine. Okay? And here we're gonna have our sigmoid test 1. So I think we better use the linear scenario here, not the sigmoid, let's remove this. This is not a good example to test the sigmoid. We better use the linear test we had before. What is the linear test? I suppose it is in example 9, linear SVM. Yeah, it is in here. So this is our linear test. So copying, bringing here to sigmoid test.r. I'm going to copy, paste, and here loading my sigmoid svm.r, and of course testing my sigmoid over here. Why? Because it's the same as a linear kernel, but it's going to affect the way I produce the results for my space in terms of my kernel. You're going to see it. So here we're going to call svm sigmoid, and we have to provide sigmoid, yeah, and we have to provide some gamma. We have to provide some coefficient. Yeah, I think that's all. So here you're gonna get like you know, gamma equals to 1 to start, and coefficient equals to 0. You guys can try so many different combinations. That's something that I leave for you as part of our class. Please try those possibilities. Now here we have the same. We're gonna plot, of course, like this. Yeah, there's no big deal. And the classification is not classify, it's classify.sigmoid. I think that's all. Of course, yeah, I'm gonna leave this. Yeah, I'm gonna leave this. Before applying the sign I mean applying the sign function without applying the sign function. I'm gonna see the results. Of course, loading up my sigmoid test and running sigmoid.test1 like this. Of course, we're gonna get here. You know what? I think we should have. Let me see. That's a hyperplane, but let me see. Yeah, that's interesting. Yeah, that's good. Yeah, it is. It is good. I use gamma equals 1, and here we've got points around 10, minus 10, minus 10, n plus 10, plus 10, and most points were used as support vectors, as you guys might notice. Why that? Because gamma was set as 1. Can I understand why, if I open gimme-plot and I use the same transformation, like hyperbolic tangent of some gamma, and let's use gamma equals 1, times some x, which is the result of our dot product, plus some coefficient that's 0. I'm gonna get this. You can observe, you might observe my function. What happens if instead of gamma equals to 1, I use like gamma equals to 2? Take a look at the slope, or how steep is my curve. If I use 5, if I use, instead of 5, if I use 50, take a look. Wow, it's going to be almost like a Heaviside function. So the greater gamma is, the less support vectors will be used. Is that your point, professor? Yeah, let's try. So if I try gamma equals to 50, we still have like many points. I'm not sure if I'm using gamma properly here. Let's see my code over there. All the remaining is right. Maybe I'm not using gamma. I just don't remember. Oh yeah, gamma is here. Okay, gamma is here. Okay, so I'm using some gamma, I'm getting some gamma back, and of course I have to apply that particular gamma value later. So it's not gamma. What is it? Let's see. Let's see my test. Yeah, sometimes things happen, as you know, guys. Sometimes we make mistakes. Okay. You know what? I think I will just consider like this. Gamma equals to 1, but I will just make my means. Let's see how I plotted. I decided to plot. Yeah, I could change. I could use my means like this. Minus 20 to plus 20. It's still using many points, guys. So it's not the best actually. Somehow gamma and like coefficient. Coefficient is not affecting here. but the gamma is affecting unclassified sigmoid. But you know what? We just print here what is the value for gamma, because I'm not sure if I'm using the gamma properly. Yeah, let's do like this. Let's run. Still considering -10 and 10, and gamma 1. Yeah, gamma is 1. Is right, at least is 1. Let's try what? I'm going to reduce actually. Oh yeah. I'm going to reduce gamma. Sorry guys, it's the opposite. Sorry, that's my bad. You know why? Because I have to reduce the result of the dot products. If I reduce, of course, by reducing, I will bring, let's use gamma here equals to 1, still equals to 1. When I reduce, of course, this axis is the result of my dot products. As those values are very large, because all elements are like -10, -10, and +10, +10, that makes, of course, the relevances to match somehow nearby my hyperplane, so I consider more support vectors. So if I reduce gamma, the opposite is going to happen. Like gamma equals to 0.001, I have a single hyperplane, a single support vector on the positive and a single support vector on the negative side. And then we're going to have, of course, two x's that are a little relevant, but it's still like 10 to -16. That's not really relevant, you know, guys. And this is our hyperplane, and this is the effect. Take a look. All this and this, well, this was something I wanted to show you. This is positive, this is negative, and this is some transition from -1 to +1. You can see there is no gradient after reaching 1, it's 1 forever. After reaching -1, is -1 forever. There's no gradient as before for our linear kernel. Okay? Of course, we can adapt the parameters and test for different parameters. I'm going to leave you guys with gamma here set up as 0.1, so you can test it just like this. You can just reload, just load your code, actually the code we wrote together, sigmoid, support vector machine, and test. In this scenario, of course, you're gonna get 1 as gamma. No, gamma shouldn't be 1, guys. Let me leave this. I'm gonna open again and reload my code. It shouldn't be 1 because I set 0.1. Saved. Yeah, I saved. At least it's good. So I'm going to load sigmoid. It's sigmoid test. I think I loaded the other file. So sigmoid.test1 and I run it. Oh yeah, that's perfect. It's running properly. You guys will see the result. I'm going to take some time to update my plot, to refresh my plot. And you can reduce even more to see how that's going to change my hyperplanes. In this plot, you're going to see the hyperplane, the perfect hyperplane, just the positive and negative sides. And here you can see some gradient, some transition. When it's 1 forever. When it's -1 forever, this is somehow this uncertainty region nearby the hyperplane. Okay? So when you change gamma, you basically change the uncertainty region. You say how wide is going to be this uncertainty region. That's nice. So guys, that's all for now. See you in the next video.